Hello students and welcome to the lecture. So students, as you can look here that basically in this lecture, we are going to start our discussion over the gravitation. This is going to be a topic for the discussion for this lecture. In this, we will discuss the gravitation part 1. Okay. Like many times, we have heard this word gravity, and what we generally understand by saying this word is that it is attractive, right? Generally, we see this. Like you can say if you throw a ball upside in the air, the ball will come to the earth. Even if you jump upside in the air, you will come to the earth. So we generally assume that gravity is a force of the earth through which the earth attracts everything towards it. That is what we understand, right? Basically, in this lecture, we are not only going to focus on this understanding of ours regarding the gravity, but we will try to go much more deeper into this concept, like from where the discussion over the gravity was actually started, what were the developments, what were the observations on the scientific facts and figures that we obtained over the period of time, and how all these things work in reality, not in a common language that we use often, but in the scientific terms. Okay. In this lecture, we are going to talk about the introduction first, Kepler's laws of planetary motion, gravitation, variation of acceleration due to gravity, relationship between capital G and small g that we often see while we talk about the gravitation, what the meaning of these symbols exactly. And at last, we will see the summary of all of these. Okay. But before this, there is a small disclaimer that we require to understand first. The disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the image. Now let's begin with the topic. So it's a time for the introduction of this gravitation, how all this was started. So we could say that actually that was the 5th century AD, when there was a famous Indian astronomer and the mathematician. His name was Aryabhatta. Actually, he studied about the motion of celestial bodies. Now you can see here the celestial bodies. Okay. So what do we understand by the celestial bodies? Celestial bodies actually are the universe body, like the planets, like the earth, like the moon, like the sun, like the stars. All these which are present in our universe, in our space, that we call as a celestial body. So he was studying about the motion of celestial bodies, like how these celestial bodies moves. And after observing this, after studying this, he wrote his conclusions in his book called Aryabhatta. Okay. He established that the earth actually revolves about its own axis. Okay. He said the earth is having its axis and it is actually revolving on that particular axis. Okay. That was his some of the observations. We are not going to discuss the Aryabhattam, the book that he wrote. Now we are just taking it into the consideration while we are trying to understand the gravitation and how all this was started. Okay. He also gave the description of motion of other celestial bodies that was seen from the earth. Like you can say, we're talking about the 5th century. Most probably on that time there was no telescope. By virtue of this, we could see the things, okay, in the space and all. So the things that are visible from the earth and those were celestial. So he tried to give a description of motion regarding those things also. Okay. After him, the another important key figure that is here is Galileo. So basically, Galileo was the first to recognize the fact that all bodies, irrespective of their masses, fall towards the earth with constant acceleration. Like he said, suppose if there are two bodies that are being attracted towards earth, okay, then these bodies will fall towards Earth with constant acceleration. Their mass will not be a defining factor in terms of their acceleration. So you could say, suppose if you have thrown two stones, one is for 10 kg, one is for 5 kg. These two stones will be on Earth or will be attracting towards Earth with the constant acceleration, irrespective of their mass. Okay, so Galileo was the first who recognized this fact and who provided us this fact. According to him, he said each body is accelerated equally towards Earth, which means if we're talking about two body, 10 kg stone and 5 kg stone, when we drop them, both of them will come towards Earth with constant acceleration. Okay, it will not be there like the 10 kg comes fast or the 5 kg comes fast. No, both will come with a constant acceleration. The value of acceleration due to the gravity, the acceleration that is being generated in these stones because of the gravitational force of Earth, that is obtained by the Galileo in that time, and that value which he gave during this experiment is actually very close to the more accurate value that we obtain later in the modern time. During the time of Galileo, Tycho Brahe, okay, they were from the Denmark. They spent his entire lifetime in recording the observation of the planets with naked eyes, which means he did not use any telescope and any other device to see the planets, but just by his eyes, he tried to observe the planets and wrote down his conclusion. Basically, the data that he provided by spending his lifetime in observation of this planet, his data later got analyzed by the Johannes Kepler. Okay, Johannes Kepler was the person who, after analyzing the Tycho Brahe data, formulated the three laws that are famously known as the Kepler's laws of planetary motion. Okay, and these laws later on are used by the Newton. Here you can say that knowing three laws of planetary motion, Newton basically proposed his universal law of gravitation, which proved later on of a greater importance. So now we could say first Aryabhatta observed several things. Then Galileo came into the picture. Thereafter Tycho Brahe was there. Tycho Brahe's data got analyzed by Johannes Kepler, and Johannes Kepler proposed the three laws that are known as the Kepler's laws of planetary motion, and these three laws were later on used by the Newton to propose a universal law of gravitation. Okay, so that's how all the things began in the starting. Now, if we talk about the Kepler's laws of planetary motion, so the first law that he gave, it is known as the Kepler's first law, also the law of orbits. He said all planets move in an elliptical orbits with sun at a focus. Kepler's first law is based on inverse square law. In figure, you can see the closest point P called perihelion and the farthest point A called aphelion. The length PA is equal to AO is called the semi-major axis of the ellipse. Now just track them one by one. Now you can say this is the planet. In the picture you can say this is the sun. You can say. Okay. So now you can say the planet is having its own orbit. Okay. It is revolving around the sun. Within this orbit, it is not getting there. It is not getting there. Not getting close to the sun. Not getting far from the sun. It's having its fixed elliptical orbit. Why we are seeing elliptical? Because it is not circular. If you look at it here, you will find out this is not circular. This is elliptical. Okay. And that was actually based on the inverse square law. All right. And P point here you can say, if you look at the distance, you will find out that this is the shortest distance. It is known as the perihelion. If you look at this point, you will find out this is the farthest distance known as the aphelion. Okay. So when the planet is closest to the sun, it is known as the perihelion. When it is farthest from the sun, it is known as the aphelion. And the length of PO is equal to AO is called the semi-major axis of the ellipse. Okay, so that is about his first law, law of orbit. Second law that he gave, known as the Kepler's second law or law of areas. He said the radius vector from the sun to the planet sweeps equal area in equal time. Therefore, the area velocity of the planet around the sun is constant. Okay, so you can say basically if this is the sun and this is the radius. Okay, so that is fixed in number, and the coverage of this radius is also fixed, like equal area in equal time. That's why the velocity of planet by revolving around the sun will remain constant. It is not like sometimes it is much more higher, sometimes it's neutral, sometimes low, sometimes it's very much low. Not like that. That will remain constant. Okay. Kepler's second law is based on the law of conservation of angular momentum. Okay. Like the planets revolving around the sun with constant velocity, not higher, not lower, with constant velocity. After this, he gave his third law, known as the Kepler's third law or law of period. He said the square of the time period of a planet is proportional to the cube of semi-major axis of the ellipse. Okay, so the more the radius, the more the time. T square equal to R cube. So you can say, as we know, if the planet is having the close orbit towards the sun, then what will happen? The revolution time the planet takes while completing the one revolution is lower in comparison with the planet which having the radius, or you can say high orbit radius in comparison with the sun. Okay, so that planet will take more time while completing the revolution, and this planet which is having the shorter orbit takes less time while completing the revolution. Okay, so T square is equal to R cube. That was the third law. So there are the three laws: law of orbit, having the fixed orbit; law of areas, the area is fixed, the velocity is constant; third is law of period, the more the area of the radius, the more the time will take. Okay, where T is time period, therefore the time taken by a planet to go once around the sun. It means that to complete the one revolution. R is equal to semi-major axis of elliptical orbit. Obviously, those planets which are far away from the sun having a large period of revolution. Why? Because their radius around the sun is higher. Okay. The planet which are nearest to the sun, like the Mercury, they having the period of revolution of just only 88 days. While the Neptune, this is the Neptune, this is the Mercury. Okay. So Mercury takes only 88 days while completing the one revolution. Now you can say if we try to draw the you can say elliptical orbit of Neptune. So radius now you can say is much more higher. So that's why Neptune takes almost 165 years in just completion of one revolution, because the area or the radius is much more higher in comparison with the Mercury. Okay, so that was the observation of third law of the Kepler's. Okay, now let's talk about the gravitation. We have taken the consideration of introduction, like how the things were started in studying. Thereafter, we also take the introduction of the Kepler's law. Now it's a time to talk about the gravitation. Okay, so gravitation is actually the name which is given to the force of attraction between any two bodies of universe. Like you can say, if you see any two bodies of the universe, these body having the attraction force between them, this is known as the gravitation or the gravitational force. Actually, this force was discovered by the famous scientist Newton. also known as Sir Isaac Newton. In the year of 1665, he discovered this because he saw the apple falling down the tree. Or there is a very famous story associated with this, if you ever heard about it. Like Newton was sitting beside the apple tree, then apple from the tree plucked on his head, and after seeing this apple, he thought that there is a force of attraction and all. This is the story. Most of you have heard about it. Okay. So in 1665, he saw that the apple falling down the tree, coming towards the earth, from where he got an idea about this force of attraction. Later on, after discovering it, he named it as a gravitation. Gravitational force is actually the weakest force among the four fundamental forces of nature. Okay, what are these four fundamental forces of nature? Gravitational force, electromagnetic force, weak nuclear force, and strong nuclear force. Amongst these forces, gravitational force is the weakest force. Okay, but apart from this weakness, it is the most important. Why? Because it played an important role in initiating the birth of stars and controlling the entire structure of universe. This entire structure of universe, how the stars born, why we are revolving around the sun, all these things could be explained by only understanding of gravitational force. Okay. So he gave his Newton's law of gravitation. So the force of attraction acting between the two bodies is actually directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So you can say, suppose if there are the two bodies, M1 and M2. If M1 having the lesser mass in comparison with the M2, okay, so the both will have the force of attraction between them. But the force of attraction of M2 will be higher in comparison with the M1. Why? Because the mass of M2 is higher than the M1. Okay. So directly proportional to the product of their mass. Inversely proportional to the distance. When the distance will be lower, the force of attraction will be higher. When the distance will be more, the force of attraction will be low. Okay. The force acts along the line of joining the two bodies. Like here you can say, this line that you are seeing, this is actually the force of attraction being applied on both the bodies, M1 and M2. In figure, let there be two bodies of masses M1 and M2 at a separation point of R. The magnitude of force of attraction F acting between them is, F is directly proportional to the M1 and M2, and F is inversely proportional to 1 by R square. So this is the observation. And you can say F is directly proportional towards M1 into M2 by R square, or F equal to G into M1 into M2 by R square. Okay. Now, let's talk about the capital G, which is known as the universal gravitational constant. So where capital G is actually the constant of proportionality, which is famously known as the gravitational constant. The value of G remains same at all places, and it is independent of the nature of particles, temperature, medium, etc. That's why it is known as the universal gravitational constant, which means while changing of the place, changing nature of particles, temperature and medium, this value of gravitational constant could not be affected. That will remain as it is. Okay. Therefore, it is the universal constant and known as the universal gravitational constant. Why? Because their value is constant and same at every place with every nature of particle, temperature, medium and all. Got it? The direction of force F12 on mass F1 is towards M2 along the line joining the masses M1 and M2, whereas the force F21 on mass M2 is towards mass M1 along the same line. Here you can see in this figure. Both these forces are equal in magnitude but opposite in direction. Okay, like the attraction force the M1 is applying on M2 and the M2 is applying on M1, that is of the same magnitude. But the direction will be different. Like M1 is applying the force in the east direction while M2 is applying the force in the west direction if we talk about the direction. Okay. So magnitude will be equal, but direction will be opposite. Thus, it is an action-reaction force. Okay. Like same magnitude but opposite direction. SI unit of G is Newton meter square kg is minus 2 power. And its value is 6.67 into 10's power minus 11 Newton meter square kg's power minus 2. Okay. There is a note. The gravitational constant G is actually numerically equal to the magnitude of force of attraction between two masses, each of 1 kg placed at a separation of 1 mx. Importance of the law of gravitation. Why this law is important? So Newton used this law to explain the motion of planets around the sun, the motion of the moon, which is the natural satellite, why the moon revolves around the earth, and the motion of any freely falling body. Like why every body under the influence of the gravity falls freely towards the earth. Why this motion actually happens. So all these things got explained by Newton because of this single law of gravitation. Okay. Now, force due to the gravity, if we talk about it, according to the law of gravitation, the earth attracts each object around it towards its center. So, from here, the earth attracts moon also and everything that is on this earth that is in the gravitational pull of the earth. The earth attracts all the things towards its center. If we go by the law of gravitation, the force with which the earth attracts a body, okay, towards the center is actually called the force due to the gravity on the body, which could be taken to act vertically downwards at the center of gravity of the body. Like this center, now this is. Okay. In vertical motion near the Earth's surface for height much smaller than the radius of Earth, the force of gravity on the body is assumed to be the same throughout. But if the distance is more than radius of the Earth, then that will not be that much same. The force due to the gravity on a body of mass m capped on the surface of Earth of mass m and radius r is equal to the force of attraction between the Earth and that body. Which means the force of attraction the Earth applies on that body is equal to the force of attraction the body applies on the Earth. It is given as F equal to g m into m by r square. Taking the mass of Earth, m is equal to 5.96 into 10's power 24 kgs. Radius of Earth is r is equal to 6.37 into 10's power 6 meters. Meter is equal to 1 kg if we go by this. And the universal gravitational constant, the capital G is equal to 6.67 into 10's power minus 11 Newton meter square by kg square. Then F will be equals to 9.8 Newton. Thus, the Earth attracts a body of mass 1 kg by a force of 9.8 Newton towards its center. So we could say if there is any body of mass 1 kg that will be attracted by the Earth with the force value of 9.8 Newton towards the Earth's center. There is a note. As Earth attracts an object towards it, the object also attracts the Earth towards it by an equal force. Okay. Since the object is free to move, it starts moving towards the Earth, but the Earth, because of large inertia, does not move towards the Earth. Like you can say, if you look at this picture, this is the moon, this is the Earth. They both are applying the force on each other. The moon could easily move. Why? Because it's having the smaller size and low inertia, while the Earth is having the massive size and high inertia. That's why the Earth that not much easily moves. Difference between the gravitational and the gravity. If we talk about the difference between the gravity and the gravitation. So we could say gravitation is actually the force of attraction that is acting between any two bodies of universe. Okay, any two bodies, any two celestial bodies which are attracting each other towards their center. The force that is being working there, it's known as the gravitation. While the gravity is in the Earth's gravitational pull on a body lying on or near the surface of the Earth. That is known as the gravity. So, the direction of gravitational force on body A due to the body B is along the A into B. The direction of force of gravity on a body is along the line joining the body and the center of the Earth and is directed towards the center of the Earth. The force of gravitation between two bodies could be zero if the separation between bodies becomes infinity. Because we know the force of gravitation is actually depend upon the distance between the two bodies. If that distance become infinity, then it means the force of attraction between two bodies would be zero. The force of gravity on a body is zero at the center of the Earth only. Because now the body reached the center of the Earth and no force will be applied then. Now, the acceleration due to the gravity. So basically, it is the rate at which the velocity of the freely falling body increases. Then it is known as the acceleration due to the gravity. In other words, we could say it is the acceleration produced in a free falling body due to the gravitational force of attraction of the body. Like you can say, this is the ball. At first, the ball starts from rest. At second, it is covering the 9.8 meter per second. Third, you can say it's acquiring the speed of 19.6 meters after 2 seconds. Now you can say the speed of falling this ball, which is falling freely in the influence of gravity, is increasing, right? So this is actually what we call as the acceleration due to the gravity. Okay. Acceleration due to gravity does not depend on the mass, size, and shape of the body. Remember this, remains constant. The acceleration due to gravity is actually denoted by the letter G, small g. The SI unit is meter seconds power minus 2. It is actually a vector quantity directed vertically downwards towards the center of Earth. Experimentally, it is found that the value of acceleration due to the gravity G does not remain constant at all. That will change while moving freely. On the Earth's surface, the value of G varies from place to place. Okay, that is not constant and not equivalent towards all the places of the Earth. Okay, so Galileo was the first scientist to study the motion of different bodies under the force of attraction of Earth, therefore the gravity. From his experiment, Galileo found that if bodies of different masses and size, also in the shape, these are simultaneously or with together made to fall in vacuum. Therefore, the absence of air and any kind of friction and all. And they have been fallen off from the same height. Then they all reach the Earth's surface simultaneously and with the same velocity. Which means the shapes, masses, size do not differ it in vacuum when the absence of air is present. Okay. So if they start together, they will reach the Earth together. Thus, all bodies travel the same distance in the same interval of time. Moreover, he found that velocity of a freely falling body does not remain constant, but it is increasing at a constant rate. Now, the variation of acceleration due to the gravity. The value of acceleration due to the gravity changes with height. Therefore, the altitude, depth, shape of the Earth, and also the rotation of Earth about its own axis. So these factors, actually the factors that changes the value of acceleration due to the gravity. Now the effect of altitude. At altitudes above the Earth's surface, the value of G decreases. Therefore, the value of G decreases with height. Like the more the height will be, less the value of G will be. G is equal to G into R square by G into bracket R plus H square equal to G into 1 minus 2H by R. R plus H whole square is there. Okay, just look at it. Note, at the height equal to the radius of Earth, therefore, H is equal to 6,400 kilometers. G will be equals to G is equal to G into R square by R plus H whole square equal to G into R square by R plus R whole square is equal to G by 4. Now, effect of depth. The value of G decreases with the depth. Gn is equal to 1 minus D by R. At center of the Earth, D is equal to R. Okay. And G is equal to G into 1 minus R by R is equal to 0. It means the acceleration due to the gravity G is 0 at the center of the Earth. Effect of shape of Earth. Earth is actually not of a perfect sphere. Okay, like many times we see that Earth is circular, but it's not actual. Okay, it is flattened at the poles. If you look at here, you will find it is flattened and bulge out at the equator. This is the equator. You can say it is bulge out. Equatorial radius RE of the Earth is about 21 kilometers greater than the polar radius of RP. As we know that G is directly proportional to 1 by R square. Therefore, the value of G is least at the equator and maximum at the pole. Got it? It means the value of acceleration due to the gravity increases as we go from equator to the pole. Okay? Because at equator, the distance from the center to Earth is higher in comparison with the distance from center to pole. Note, at sea level, the value of G of poles is greater than its value at equator by 1.80 centimeters seconds power minus 2. Effect of latitude due to the rotation of Earth about its own axis. So, latitude at planet is defined as the angle which the line joining the place to the center of the Earth makes with the equatorial plane. Here you can see. Okay. This is like you have seen the latitude. Okay. It is generally noted by this letter, and in figure you can say latitude at a place equal to this one. Okay. At pole it is 90 degree. At equator it is 0 degree. Acceleration due to gravity G decreases on account of rotation of Earth. G is 1 equal to G minus this one. If rotation of the Earth increase 17 times of the present value, then the weight of a body at the equator becomes 0. Okay. If the Earth stop rotates, then W is equal to 0 and G1 is equal to G. Obviously, the value of G increases on decreasing the value of angular velocity of the Earth, as well as the vice versa case will be there. Acceleration due to the gravity increases with the increase in latitude of the place. At equator, latitude is equal to 0 degree and cos equal to cos 0 degree, and then G is equal to G minus R into W square. Clearly, gravity on equator is minimum. At poles, it is like this. So you can say gravity at pole is maximum. If a body taken above the surface of Earth, the value of acceleration due to the gravity varies inversely as the square of distance from the center of the Earth will be increased. But if the body taken inside the Earth, the acceleration due to the gravity decreases linearly with the distance from the center of the Earth. The rate of decrease of the acceleration due to the gravity with height is twice as compared to that with height. The value of acceleration due to the gravity is minimum at planet Mercury and maximum at planet Jupiter. If the rate of rotation of Earth increases, the value of acceleration due to the gravity decreases at all places on the surface of the Earth, excepting the pole. If Earth stops rotating, there will be increase in the value of G at equator by a value, this one, but there will be no change in the value of G at pole. According to the Einstein, there is equivalence between the gravitation and acceleration. This idea led Einstein to predict general theory of relativity, which could explain gravitation effects in terms of the curvature of space. Now, the relationship between the universal constant of gravitation and the Earth's gravity, or acceleration due to the gravity, sorry. Consider Earth to be a spherical body of mass m, radius r with center O. Suppose a body of mass m placed on the surface of Earth, where acceleration due to the gravity is g. Let F be the force of attraction between the body and the Earth. Then, according to Newton's law of gravitation, F is equal to gm into m by r square. From Newton's second law of motion, we could say m is equal to mg is equal to gmm by r square, or g is equal to gm by r square. From the above equations, we note that the value of acceleration due to the gravity is independent of mass, shape, and size of the body, but thus depends upon the mass and radius of the Earth. Mass of Earth is equal to 6.018 into 10's power 24 kgs. Density of Earth is equals to 5.5 into 10's power 3 kg minus cube. This expression for acceleration due to the gravity in terms of radius and density of the Earth is given by this. Now we have finished the topic. It's part for the summary discussion. We have talked about the Aryabhat, Galileo, Tycho Brahe, Newton, Johannes Kepler. We also discussed the Kepler's law of planetary motion, like law of orbits, law of area, law of periods. We also discussed about the Newton's law of gravitation. Gravitational force, acceleration due to gravity, we have discussed. Effects on G, altitude, depth, shape of Earth, latitude, we have discussed. Einstein general theory of relativity, we have discussed. Value of G as independent of mass, shape, and size, we have discussed, but depends on the Earth mass and radius. Standard value of G at 45 degree latitude and sea level that we have discussed is 9.8 meters second square. With this, we have finished this part. It is requested to all of you, kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.